Okay, so let me first remind you, we were talking about, we're talking about, we're talking about valuations. Say V came on 0 to G. Such that number one, and and so we looked at a number of examples of these with valuation domains. We looked at a number of examples where my totally ordered ability group was the integers. We looked at an example where the totally ordered ability group was the rationals. And we looked at an example where the totally ordered ability group was two copies of the integers ordered less subtracted. Right. So here is a theorem, and I want to put this back up here to kind of help with that. Well, thank you. Let K be a field of the evaluation. The set of elements X and K really such that is a valuation domain. And it is called often the valuation domain associated to this particular valuation V. Now, let me clear something up, I hope, in this theorem first, and that is when I say V of X is greater than or equal to 0, what I mean is it's greater than or equal to the identity of the totally ordered ability group, right? So for example, with the example of lexicographic ordering, the identity of 0, 0. So let's prove this. And the proof is a statement here. It's fairly straightforward. And that is note if X and Y are in V, and let's take V be not 0, right? Because certainly if either X plus Y, if either X or Y is 0, then we add them and the sum is still in there. Then if X plus Y is 0, then X plus Y is in V by definition, and if not, then the value of X plus Y is greater than or equal to the min value X, value Y, and since neither of these are 0, this is greater than or equal to, right? So And of course, again, if either X or Y is zero, it's clear that the sum is in B. All right. So this is closed under addition. Also, if X, Y are non-zero, then and again, it's clear that if X or Y is zero, the product is evaluation domain contains zero. So this shows so B is a domain, right? And the reason is because it's a ring and it's a subring of a field, so it has to be an integral domain. And the last thing is, I'm going to claim, I claim something that's maybe implicit in this, but it's a little bit stronger, and that is, I claim that B is a valuation domain and its quotient field is K. So let omega be in K, say it's not zero, if omega, the value of omega is greater than or equal to zero, then omega is in B. And if value of omega is less than zero, then value of omega is greater than zero of inverse. Right, because B contains everything of positive value. Right. So this shows that actually B is valuation domain. Okay. Any questions on that? Okay. So now we're going to build on this. So we've got some big things out of this. We've got some constructions of valuation domains. We know what valuation is. And we have this connection between interval closure and valuation domain. This brings us to how many of you in your encounters have encountered invertible ideas? Right? In a number of different contexts, I suspect most of it. Right? Have you? Oh, yeah. Oh, so this will be fun for you. All right. So invertible ideal generalize principle. And they generalize ideals, they generalize in particular principle ideals. They're in a certain sense, in fact, in the rings that I like to look at, there's an intimate connection between invertible ideals and principle ideals. So, for example, well, I'm going to give two examples. Probably not too soon on that. So let me give you a definition here. All right, so I'm going to have to define what's known as a fractional ideal. Let R be an integral domain. Of course, it's okay. An R submodule. If I in A is an R module. So I is just some R submodule of the quotient field. In fact, at this point, I could even have I could have I be R, or I could have to be the entire quotient field or whatever. This is called a fractional ideal. If there exists a non-zero A and R such that A I is equal to I. Right. So let me look at some examples here, and then I'm gonna kind of beat this down. Example. Any item. Any ordinary ideal is fractional ideal, because if you take any, so suppose I inside R is the ideal that you're used to. This is certainly contained in the quotient field because it's contained in the domain. And it's an R module because any ideal is an R module. So there you go. And you can take A to be 1, right? Because if it's already in there, then you're good to go, right? So any ordinary ideal is a fractional ideal. Well, that's good. So this definition isn't completely stupid. But there's other ones. So for example, or there can be other ones. Is a fractional ideal. I think we could all agree that this is contained in the rational numbers, that it is closed under addition and multiplication by elements of Z, right? This one, though, is not an ordinary ideal, right? Because it's not contained in Z. What A works for this? 2, for example, or you could have gone 4 or 8 or 6 or whatever you like, right? Any of those, right? Here's the thing that's maybe confuses people sometimes about fractional ideals. In ordinary ideals, you used to be able to take 2 elements, the ideal, multiply them together, and they're in there, right? You can't do that with this ideal, right? Because, for example, 1/2 times 1/2 is 1/4, which is sort of even worse. It's got a bigger denominator, right? However, if you think about ideals this way, if you think of ideals as R modules, the only reason that the product of 2 elements in an ideal is still in the ideal is because one of those elements is in R, right? And so ordinary ideals, all your elements are in R, and you don't have to worry about this. Out here, you're only left to multiply by elements of the ring, which make it no difference in the original if it's an ordinary ideal, but here it does, right? Can you give me a Z submodule of Q that is not a fractional ideal? Q is not. Can we prove this? once more, any excuse to talk about factorization, right? So suppose it is. Well, I certainly already know that Q is a Z submodule Q, no problem there, right? But really, the key here is, can we finally say well, factor A into primes. A equals P1, P2, Pn with E1. Factor this into positive primes here, and these primes need not be distinct. However, there is the biggest one. Let Q supposed to be a big one. Notice that A 1 over Q is not a good. And there you go. It's impossible for this to be a fraction like it. And actually, I do this example for a purpose, and the purpose is to kind of justify this. Why do we have this condition here? It's a finiteness condition that we will need for some of our results later. What this condition says, you can find a non-zero A and R such that AI is contained in R. I is this big orgy of fractions, right? And A is a common denominator that sweeps everything out. You can think of it that way. So what this means in a certain sense is I consists of fractions because it's in the quotient field, but all of those fractions can be found to have the common denominator A. So things don't get too big, too out of hand, right? Okay, any questions? So here's another definition. And here I'm going to define what's known as the inverse. I've done this notation also in terms of colons as well. Maybe I'll recouch it that way. Let I, or we have quotient field K, and I and K a fractionalized. We define the inverse of I thusly. Okay, so the inverse of I is going to be a collection of everything in the quotient field. Gather it all up, all the stuff in the quotient field, such that Xi is contained in R. So one way that you might think about it is this is a collection of all denominators that you might have, right? Now I'll give you an example where I'm kind of using that terminology loosely a little bit, but we note here that when you multiply I times I inverse, now remember, I times I inverse, well, that should be a module, right? It's the sum of all products alpha, beta, where alpha lives in I and beta lives in I inverse. But check this out. If X is in I inverse, multiply anything in I, it lands back down in R. So in fact, this is always contained inside of R, and it's also an R module, so it's not healing. So by the construction of I inverse, this is always the case. If I inverse is equal to R, we say I is invertible. This is what we need for the ideal environment. Something else I want to say about that too. Oh, right. Another way, I inverse, sometimes written this way. This is a conductor notation. This means all the crap in K that blasts I into R. Right, and that's what this definition is. It's all the stuff in the quotient code K that blasts I inside R. So let's look at some examples. Let's say I equal 2/3 Z. Right, so this is 4/3, 2/3, 0, 2/3, 4/3, 2, 2/3, 7/3, 4. Anybody? Okay. I inverse. So this is all the crap that blasts this. So this is all possible denominators. Again, using that terminology loosely. Let me point out that any multiple of 3 works. Right? If you have any integer that's a multiple of 3, there you go. You're back in the integers. But can you do better? Any ideas? There you go. Because if I use any multiple of 3 and blast that back in, notice that everything in the image back in is a multiple of 2. So actually, I don't have to. So my denominator, in a certain sense, can be 3 halves. Notice that if I take any 3 halves times an integer and multiply it times 2/3 of an integer, I get an integer, right? And notice in this case, so this is actually an invertible idea. Now, here's kind of an important step in math. My next question is, there's probably nothing really special about these wacky fractions that I picked. Can we generalize this? So let me be bold and generalize this to a domain. We have quantum field. Let me, so here's what I'm asking. Can anybody give me a large class of ideals that are always going to be invertible? I mean, look at this example and see if you can derive any principles from it. Yes. Principle. And let me be super anal about that. How about non-zero principle? Right. So let 0 in R. Then XR is a principal fractional. And anybody want to take a bold guess as, in this case, what do you hope it is? And notice that in this case, I inverse equals XR, X inverse R, which is R. So notice, here's what we can glean from this. Any zero principal ideal of a domain is invertible. So let me throw in kind of a little unnumbered theorem here. Claim and this will actually illustrate something for us. Suppose R is a principal ideal domain. Closer to it. I'm going to make the following bold claim. Then all fractional ideals okay. No shocker so far that the ordinary ideal principle, because that's what it means by ideal domain. But the question is how do you know if you've got a principal ideal domain? How do you know there's not some fractional ideal that's not principal? Any idea? Let me call it the fractional. And I would like to make a bold claim that this is in fact generated by a single element as a module. Yeah.
Oh, it's in A such that AI is contained in R, and that's going to be principal. Best.
So in fact, and there you're using the principal ideal domain business. And so I'll leave you step out to show I is excellent, right? It's pretty easy to show if you get the second thing that you want. So in fact, what this shows is that if you have a PID, my arbitrary fractional ideal was principal, right? And we already know the principal ideal is invertible. So for a principal ideal domain, every non-zero fractional ideal is invertible. Right? This is not true in general. Can you think of an interval domain? I guess it must be necessarily not a PID, where you have an ideal that's not invertible. I think it's good to go through this exercise here. take a polynomial ring over, by the way, I'm gonna need two variables, because if it's just one variable, that's a PID. So this example sort of expresses that invertible ideals kind of fell quickly. In this case, the function field, rational functions in X, Y. I claim maximum ideal M I claim that this is not invertible. And I'll try to show you some decent details. We'll probably won't out too much on this. Okay. Let us figure out what the inverse of this is, right? So well, this is the setup, let's say Z in quotient field. Such that Z times N is contained in R. Right. So in particular, let me point out that M inverse must contain every single element of R. For sure, it's got that, right? Is there anything else? Well, let's see. Suppose, notice this is, of course, contains R. Right? Suppose f of x, y over g of x, y is an M inverse, but not an R. So, what do we know? G of x, y is not constant. Right, because if it were constant, then that already be back in R. And by the way, what other assumption? What spell should I be casting here? What other assumption should I make? It's probably the greatest assumption I can make in the circumstances.
The fraction is anyways.
Okay, right. Let's assume that greatest common divisor. By the way, let me be again super careful. How is it that I can make that assumption? What do I know about R that allows me to do that? It's not quite included when you get too many variables. But you don't need that much. It's a unique factorization domain, right? And so you can factor F into primes and G into primes and just cancel off everything that's in common, and what's left over will have GCD. Actually, this one, unfortunately, this domain is not basic in the following sense. If you, for example, you can take the elements X and Y and their GCD is 1. Everybody agree with that? But there's no linear combination of X and Y that equals 1. Right, so there you go. But we'll assume this, and we're good to go because the original ring R is a UFD. That's helpful. Now, notice that notice that when this multiplies anything in M, it has to be an R. So this times X and also both of these have to be in R, right? Because both X and Y are in M, and F over G is supposed to be an M inverse, so when it hits X and it hits Y, it's gonna blast back into R, right? So let's see what this gives us. This means that F F Y times F of X, Y is R times. And it also means that X F of X, Y is R2 times V of X, Y. Yeah. Okay, so anybody see what we can do with that?
G of X, comma, Y doesn't share the common factors with F of X, comma, Y. So it's trying to divide both Y and X.
Very good. Right. Notice G of X, Y divides this. G of X, Y also divides this, right? But the GCD of F and G is 1, right? And since the GCD of F and G is 1, so you're using some stuff from the past. This is also true in any GCD domain. We'll talk about that later, but G divides this product and its GCD with F is 1. So G of X, Y divides X and G of X, Y divides Y. Right? But X and Y are both prime elements. Right? Therefore, G of X, Y is constant. Because it has to be a unit if it divides two distinct primes like that. And this is there. So we can only conclude that M inverse equals R. Right? If today you think it's not in it. So M inverse equals M times R, which is M, which is strictly contained in R. So M is not important. And in fact, this is the typical situation because in general, when you give me the condition, I as a principal ideal, you're saying a lot. That's a strong condition. When you say that I is an invertible ideal, that's not quite as strong, but it's getting close. Saying an ideal is invertible. I mean, if you just walk up to a domain and start pulling its ideals out, it's probably not going to be invertible. Now, let me give you another reason. Well, let me try to go through this one in some detail. Consider this ideal in here. This is actually a proper ideal. Let me convince you of that, right? Because I mean, so what did I do? I just threw two generators in here, right? I mean, if I throw 2 and 5 and generate an ideal in the integers, I'm gonna get everything, right? How do I know this doesn't happen here, right? Well, to support this claim, suppose 1 is equal to 2 times A plus B right to negative 5 plus C plus D right. Just let's see. 1. Suppose that 1 is a linear combination of these two. Let's see what we get out of this. let me expand this out. This is really obnoxious, but once we get it out, then it's not gonna be too bad. Okay, first let me collect the terms that are just integers. I get 2a, I get c, and I get minus 5b. So let me get that right. 2ac minus 5. Good. And now let me get the crap with the radical -5 glued to it. And that would be 2b. And then I guess c plus d. Like, this looks awful, right? Because you get this alphabet soup stuff up here, but check this out. This means it's 1, it's 2a. D, and this means 0 is 2b. That's c plus d. Right? Now, I love number theory. Reduce this mod 2, and I get 1 is equivalent to c plus d, and 0 is equivalent to c plus d. You got a lot of modular arithmetic, right? So there you go. So what we've established here is this is an honest to goodness proper idea, right? I'm also going to show you something else, and that is I claim that this is not a principal idea. So claim 2. How many of you all, so let me ask you this, see what I have to go through in detail. How many of y'all have ever worked with norms for these kinds of range of integers in a number theory class with any alpha? Who has not? Okay, well, maybe I can think. You know what the norm is? Like you take a number and multiply it by its conjugate, right? Okay, so this is a tool I'll use. So norm of a plus b radical -5 is this is very useful. Are you familiar with finite properties? Right. People, very sadistic, like number theory teachers, make you work this all out, and it's just, it's death on the hot plate, right? I mean, it's awful. But when you know a little bit of Galois theory, it's easy, because what this is norm of alpha beta is alpha beta times sigma alpha beta, where sigma is the conjugation, the non-trivial Galois conjugation, and this is sigma alpha, sigma beta. Alpha beta, sigma alpha, sigma beta, which is alpha sigma alpha, beta sigma beta, is norm alpha, norm beta. And there's also following norm u is 1 if and only if u is the unit. And again, that's fairly easy to see because if u sigma u, if this is 1, then that means sigma u is the inverse of u, right? And on the other hand, this property gives you, if U times V is one, then both of these have to have one, so. Everybody okay with it? Okay, on with this. I claim this is principal. So if I'm doing a single element, then because the principal element, it must divide everything in the ideal, and so it has to divide two, and it has to divide 5. Well, the norm of a typical element here is a squared plus 5b squared. So the norm of 2 is 4, and the norm of 1 plus radical negative 5 is equal to 6. Right? So the norm of alpha must be 1 or 2. Right? To divide this by this division norm policy. But it can't be 2, because you can't write 2 as a square plus 5 times square. And it can't be 1, because then alpha would be a unit, and we've already proved that this thing is proper ideal. So there you go. So this ideal is proper and principal, right? Right. Thank you. I got excited there. Yes, it's proper, not principal. What J be this? Well, actually, you know what? This is actually equal to I, so I'm not even gonna do that. I'm just gonna square this out. What happens when I multiply these two ideals? Now, for sure, I know that this can be generated by X. -4. And maybe less, and in fact, actually less than this. This is actually equal to the ideal generated by 2. I mean, that's kind of weird, right? It's a through generator, but it actually, and let me point out that this containment is fairly easy, because 2 certainly divides everything here, right? No problem. So this contains this. How do we know that this equals 2? How do we know that the left side is contained inside the right side? Well, for that, let me point out that because these 2 elements are in this, then this means that, oh, I guess I want to subtract it. So this minus this, I get 6 is in this ideal. Right? So now I've got 4 and 6. So I've got their GCD. So I've got 2. So I get an equality. Right? So what do we have from this? So let me point out, so you can check this. See if you can check this. So in fact, 1/2 I is I inverse in this case. It turns out in this ring of integers, remember how we pointed out that any principal ideal domain, every non-zero fractional ideal is invertible, right? It turns out this is not a principal ideal domain because of this, but it turns out that every non-zero every non-zero fractional ideal of this ring is also invertible, even though not all of them are principal. And this characterizes something called Dedekind domains. And Dedekind domains are to ideals what unique factorization domains are to elements. All right. So we're going to get to this later, but it turns out that Dedekind domains are characterized by the fact that every non-zero ideal, ordinary ideal in the Dedekind domain, every proper non-zero ideal is uniquely a product of prime ideals. Just like in the UFD, every non-zero non-unit element is uniquely a product of prime elements. This was actually this actually was a consequence of failed attempts at Fermat's theorem. That's historically why we started going down that path. Okay, any questions on that? All right, well, oh, by the way, I'm doing the math club this Friday, and I'll give you kind of a little teaser Friday. I'm going to use unit analysis to show you how to get classified secrets from the United States. This actually has been done before. It's a kind of only using unit analysis. A famous physicist figured out what the classified yield of the Trinity test atomic bomb was. Just be looking at a movie. So that'll be fun. All right, y'all have a good one. We'll see you on Friday.